We're now going to move onward to contributor talk, Eleonora Lai, talking about effects of stellar wind on high mass X-ray binary spectral timing properties. So,
okay, so
set for that. I'll give you a 3-minute warning, and you can start.
So, hello everyone. My name is Eleonora Veronica Lai, and I am a PhD student at the Nicolaus Copernicus Astronomical Center. So first of all, I would like to thank all the organizers for this beautiful conference and for giving me the chance to present my work here in Cagliari. So today I will present my latest results concerning the study of the stellar wind for the case of Cygnus X-1 and how its variability affects the spectral timing properties of the source. But first of all, let me give you a brief introduction on the source. Okay, so Cygnus X-1 is perhaps the best studied X-ray binary and one of the brightest persistent X-ray sources. Although it doesn't show dramatic outbursts, it shows variability. And as you already probably know, it presents two main spectral states, hard and soft. It is composed of a black hole of about 21 solar masses and a companion star, a blue supergiant of about 40 solar masses. So due to the size of the companion star, this system is a high mass X-ray binary, and the compact object accretes via the stellar wind of its companion. It has been estimated that more than 90% of the wind mass is located in less of the 10% of the wind volume. What does it mean? It means that the wind doesn't appear as a smooth flow, but it shows strongly dense and highly perturbed regions or clamps. So depending on the position of the compact object along the orbit, part of the emission can be, of the X-ray emission can be absorbed by the wind material. So here I'm showing you 3 different situations and the corresponding spectra that I've simulated. So when the amount of the wind material between the observer and the compact object is minimum, is small, the emission is not absorbed. But when the density of the wind material increases, the emission starts to be absorbed. In the extreme case, when a clamp is between the observer and the black hole, the emission is strongly absorbed, leading to those events that we call the dipping events in the X-ray light curve. Such events primarily occur at superior conjunction, or in other words, when the orbital phase is 0. And wind absorption features can vary on short time scales of the order of minutes or shorter. And the effect of the absorption is stronger during the canonical hard state. Moreover, the wind variability can affect the orbital variability of the source. So the purpose of my project is to investigate how the variability of the stellar wind influences the X-ray spectral timing properties of the source. And to do so, I use a long XMM Newton monitoring covering about 1.5 orbits of Cygnus X-1 in its hard state. And this monitoring is composed of 4 different observations. So, here you are seeing the orbital phase coverage for this monitoring. So it starts with observation 201, then we have the 501, then the 601, and the 701 at the end. And this monitoring is very peculiar, very unique, because it covers 2 passages at superior conjunction, or in other words, where the effects of the stellar wind are the strongest. But to study the stellar wind and the effect of its presence on the spectral timing properties of Cygnus X-1, we have to distinguish between the intrinsic variability and the variability due to the stellar wind. How can we do this? A powerful and innovative method is to look at the time-resolved spectral behavior of the source using color diagrams. So here you are seeing the 4 color diagrams that I've built for each observation, for each 10 seconds data segment, I used 3 light curves in the corresponding energy bands, which define 2 colors, a hard and a soft. So when a clamp crosses the line of sight, color values change, giving this particular nose truck shape that you can see here in the diagrams. So for a partially covered source, when the column density of the absorbing material is minimum, the emission is not absorbed. And we are in this upper right part of the diagram. But when the column density increases, the emission is absorbed. And we are in this lower part of the diagram. So thanks to the color diagram, I could select those events that are not affected by wind absorption. Then from now on, I will indicate with NWA, staying for not wind affected intervals. And now it's time to show you my main results. Okay, so I will show you the power spectra and the intrinsic coherence analysis. Here you are seeing the power spectra for the first observation, which correspond, if you remember, at the first passage at superior conjunction. So the emission is more absorbed in the top panel. In the bottom panel, I'm showing you the power spectra for the second observation, the 501, which correspond to an intermediate orbital phase. So the emission is less absorbed. In blue, I'm showing you the power spectra for the whole observation, and in sky blue for the new selected intervals, not wind affected data set, for 3 different energy bands. So even though we don't see any particular change in the power spectra for the less absorbed observation, we see differences, strong differences for the more absorbed, for the power spectrum shape. And not only in the soft energy band, but also in the 310 keV. In particular, we see that at high frequencies, the power variability is strongly suppressed, smoothing out the typical double hump shape of Cygnus X-1 for Cygnus X-1 in its hard state. While at low frequencies, the variability power is enhanced. So for clamping with models, this increase in power variability at low frequencies is due to the fact that when a clamp crosses the line of sight, the column density of the absorbing material increases. But clamping with models cannot explain this suppression. So we relate this suppression to the scattering of emitted photons, changing the time of arrival at the observer. Moreover, this suppression requires a high optical depth that is not relatable to the dense wind itself, but most likely to an optically thick region that we think is located at the zone of the impact of the wind with the outer edge of the accretion disk.
About 3 minutes.
Thanks. So moreover, we can observe that at a particular frequency, the variability power for the 2 data sets is the same. So this frequency, according to clamping with models, this frequency corresponded to a typical time scale of a typical clamp crossing the line of sight. So if we assume a terminal wind speed of 2,400 kilometers per second, the clamp side, we can calculate the radial clamp sides of a typical clamp crossing the line of sight. I wanted to show you also the changes in the intrinsic coherence as a function of Fourier frequency due to the presence of the stellar wind. So as before, I'm showing you the intrinsic coherence for the first observation, the 201. Again, the one corresponding to the first passage at superior conjunction, so it's more absorbed. And for the second observation, which corresponded to an intermediate orbital phase, so it's less absorbed. In blue, it's again the total, so for the whole observation, and in sky blue, the selected one, not affected by the wind. As you can see, when there is no wind, the intrinsic coherence is very high, in agreement with previous studies of Cygnus X-1 in its hard state. But when we take into account the wind, The intrinsic coherence is strongly suppressed. As last, I wanted to show you the comparison between the two passages as superior conjunction. So we can see there is a suppression, but the degree of suppression between the two different passages is different, further indicating that the structure of the wind changes along the orbit. So to conclude, just a summary, from the power spectrum density study, we can say that we see changes in variability up to 10 keV. At low frequencies, we see that the variability is enhanced as a consequence of variations of the column density of the transiting clamp, while at high frequencies, we see a suppression, and we think it's related to scattering emitted photons, changing the time of arrivals at the observer. Moreover, we were able to calculate the radial sides of a clamp, of a typical clamp, that is between 800 and 2,400 kilometers. From the intrinsic coherence analysis, we can say that the intrinsic coherence is very high without the wind, and the presence of the stellar wind strongly suppresses the intrinsic variability. Moreover, a different percentage of suppression, we have a different percentage of suppression for different and consecutive passages of superior conjunction, further indicating that the structure of the wind changes. And thank you for the attention.
All right, let's thank the speaker. Great for staying bang on time as well. Do we have, I'll look for questions in the chat. We got a question from Rob Fenter. Do you have enough data to see if there is asymmetry around the phase of superior conjunction as you expect the matter ahead of and behind the accretion disk to be different?
Can you repeat the question, please?
Can you repeat the question, please?
I can also say the question, Mike.
Yeah, go for it.
Okay, so thanks for the talk. It was very interesting. So my question is, you show that there's more scattering at superior conjunction, which is really nice, and it's as you'd expect. But you also expect the material either side of superior, the material ahead of the accretion disk in its orbit and behind it to have different ionization properties. So I think if you had enough data, you might investigate whether or not the scattering properties at phases either side of superior conjunction were different. What do you think about that?
Up to now, like, we investigated variability for all observations, so for the whole monitoring, but maybe I can show you again. The 501 and the next observation are most likely this power spectrum, so you don't see any difference. So it's like you can see only like a slight enhancement at the low frequency, so no scattering at all. And this is like intermediate orbital phase, not a superior conjunction. While for the other passages, superior conjunction, even if I don't have here the power spectrum, we see still a suppression, and but it's different. And stay tuned for the paper because there are like more details.
Okay, thank you. So yeah, all right.
Thank you.
I think you need lots more orbits, but yeah, it's very nice. Thank you.
Do we have something from the floor, Jerome?
Yes, there is a question from Ilek.
I'm scared.
Hi, Leonora. Thank you very much for the great work and the great presentation. So my question was concerning so now you get like an idea of the size of the clamp by looking at the passing by and the flyby time. But what could be interesting is to have an idea of the number of clamps per unit volume. So could it be something you could deduce technically from the peak-to-peak variability? I'm more used actually to think in terms of absorbing column density, which which connects to the question by Rob on the ionization state also of the wind. But do you have any information on the variability on short time scale of the column density? And do you think we could, from this peak-to-peak variability, have an idea of the number of clamps per unit volume?
Okay, number of clamps, don't know yet. But I can say that this monitoring, it's pretty cool monitoring, but we have problems for the superior conjunction, passage at superior conjunction, in particular for the last one, because GTIs are really short. So it's like, even if you look at the power spectra, how could I say it, there is a balance between the choosing the time being and so the variability and the time scale. So for now, no number of clumps.
Okay, but I think the standard deviation of the column density as a function of the orbital phase could be an interesting figure, maybe.
Okay, thank you.
Thanks, but we can discuss more about it. Thank you very much.
Thank you.
All right, Federico, if you can be quick, we'll take this as the last question.
Yes, just if you have checked the lags, if there is an evolution.
If I checked, sorry?
The time lags.
The time lags, yes. We checked also this, and actually there is like, we see like also a suppression of hard lags. So we think up to now, so maybe Phil can add something on this if it's there. Up to now, we think that the stellar wind is adding a soft lag at low frequencies. And yes, stay tuned for the paper.
Okay, thank you.
Thank you.
All right, let's thank the speaker again.